Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where we are discussing concepts from individual chapters. So first, we have already completed electric charges and field chapter, and we are currently going through electrostatic potential and capacitance chapter. In this chapter also we have already completed two concepts, and the videos are available in the playlist. I will share the playlist in last once I completed this video. So you have to watch all those two videos that already uploaded in our channel. Now today what we are going to discuss, we are going to discuss about conductors and dielectrics. Once this lecture is over, you can download the PDF for this lecture. If you join our WhatsApp group, WhatsApp community, you can get the WhatsApp link in the comment below. Also, today is Saturday, so I am also reminding you that tomorrow morning 10 am we are going to give you a 30 question paper for physics only this week. From next week onwards other subjects will also be added, so don't worry about other subjects. If you are thinking other subjects are not yet started, that will start from tomorrow, day after tomorrow, that is from 1st September it will start. Now, so if you are following our WhatsApp channel, we are going to give you a question paper, a mock test one. We are calling it KPL KCET Premier League. So if you are preparing for 2025 KCET exam, then this is a must for you, and this is for completely for free. So you can download the question paper from the WhatsApp link, and you can attempt all the 30 questions that we are going to give you, and later on in the evening I will be back with the answer of all the 30 questions. So you will get a lot of time to solve all the 30 questions. Do not cheat, do not take help from Google or from your book. Try to answer as honest as possible. This is for your own good. Okay, I am repeating that this is for your own good. Also, if you are following my lectures, most of the concepts are already discussed. Some questions are obviously tricky as per KCET exam. KCET exam does not give you full easy question. There are some tricky questions as well, so that will prepare you for upcoming KCET 2025 exam. So if you are preparing for that exam, this is also very important. Also, you need to remember that whatever we are completing today, that part till today, whatever we are completing, that will be there in your exam tomorrow. Okay, till dielectrics, whatever we are covering today, that will be there in your exam tomorrow. Also, today's lecture will be not 1 hour long, it will be little shorter, because we are only focusing on smaller concepts, conductors and dielectrics. So if you are watching this video on Saturday night, do mention that in the comment below, that I am watching your video and I am prepared for KPL series. Okay, let's start with the lecture today. What all we are going to discuss in today's lecture? We are going to discuss electrostatics of conductors, we will discuss about dielectrics, we will discuss about polarization. Okay, we will discuss in detail about dielectrics. So the dielectric part is very important, not only for KCET exam, but it is for also for your board exam. Also, concept wise, this dielectric concept is very important. Not many books, not many authors cover this in detail. So I am here to help all of your queries. If you have any questions, as I mentioned, don't forget to mention that in the comment, and at the end of the lecture I will going to give you two homework question. Also, we will going to be discuss yesterday's homework questions as well. So everything will be covered in this video. After this video is over, if you have any doubt, any questions, don't forget to mention that in the comment. I am replying to all of your queries, whatever I am facing some queries. Also, I am very glad to see you that most of you are answering the homework questions. Okay, so for example, yesterday's homework question, 2-3 students already answered them correctly, and I will follow them for next one day. Okay, so if the video is going live on Saturday, that means I will reply till Sunday and maybe on Monday, because after Monday I am anyway going to give you the answers. So for this video, this lecture, whatever homework question I am giving, the answers will be discussed on Monday's video. Okay, because Sunday is day for KPL, right? So be prepared, be ready. Let's start with the first topic, electrostatics of conductors. Metallic conductors contains mobile charge carriers, namely electrons. So we already discussed about that. The metallic conductors, when we are considering a metallic conductor, it has a lot of free electrons. Okay, free electrons, and sometimes we call it sea of electrons. Sea of electrons, right? I already mentioned that once before when we are talking about electric field and charges chapter. So they have a lot of free electron. Now what is the meaning of the free electron? Let's understand that. In metal, outer electrons, that is valence shell electrons. Okay, you are already aware of what is valence shell, what is inner shells, right? Shell structure of an atom. So the valence shell electrons, okay, that the outermost electrons are free only for metals. Okay, valence shell is there for all other atoms as well, for oxygen, for hydrogen, for all elements. The outermost electrons are called valence shell electrons, but for metals, those electrons can come out of the metal pool of the nucleus and become free. Okay, and from their atoms are free to move. Now how much free they are, let us understand that. These electrons are free within the metal but not free to leave the metal. Very important concept, that is they can move freely within the metal. Okay, within the metal they can move freely, but out they are not allowed to go outside. So inside your home you can roam freely, you can go to your room, you can go to your parents room, you can go to your sister's room or brother's room. Okay, or maybe within your building, your apartment, you can go to top floor, you can go to down floor, but you are not allowed to leave, go outside. You have to stay inside your home. Okay, that is the rule. So that is the rule for electrons, right? Electrons are not allowed to go outside unless they are given permission. So how we are going to give them permission, that we are going to discuss in later chapter, electricity chapter. So how electrons can move, but for now they are only free to move within the metal, and they are not allowed to go or leave the metal. The free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different directions. So what is the meaning of that? So electrons, I have already drawn this diagram. So electrons, they are like gas. You know that kinetic theory, that all the atom molecules of a gas, they move in a random direction. So these electrons also move in random direction. Okay, in between collision they move in a straight line. The same thing happens for electron as well. You can treat these electrons as molecules of a gas, and they almost obey almost all the properties of gas, not everything, but almost all basic properties. Okay, not the complicated properties, but basic properties, and sometimes they are also called electron gas. Okay, electron gas is also very common term. When the universe was formed during the Big Bang, there were a lot of electron gas was as well. Okay, in an external electric field, they drift against the direction of electric field. So what is the meaning of that? When you apply an electric field, suppose I apply an electric field in this direction. Okay, external electric field is applied. Now what will happen? These electrons drift. Drift means slowly they will move, moving slowly. Drift means slowly moving. Okay, drift does not mean fast moving. Okay, so they will move slowly opposite to the direction of electric field, as we know that negative charges move in the opposite direction, or negative charges feel a force opposite to the direction of applied electric field. So in the presence of external electric field, these electrons move in the opposite direction of the applied electric field. Very important thing. Now electrostatics of conductors. Now let us go to few more points to remember. Inside a conductor, electrostatic field is 0. I already mentioned that inside a conductor, if you are considering an electrostatic conductor, generally electrostatic conductor we generally represented by a spherical object, but it does not need to be very spherical object. It can be a cube, it can be a cylinder, it can be a rod, but inside this electric field is 0. What is the meaning of that? No matter if you give it charge, if you charge it, if you subject it to external electric field, okay, even if you apply some external electric field, okay, the electric field lines will pass out of the metal, it will not go inside the metal. Okay, so it is free from all the electrostatic fields. So, electrostatic field is 0 inside a conductor. Okay. Now, what is the how it is happening? Let us understand that. Suppose I applied an external electric field E naught. Okay, we are not given it any charge. For charge, we have already used Gauss's law. In the Gauss's law part, we have understood that there is no charge inside. So, electric field was 0. Okay, and electric potential was constant. So, that much we already studied in our electrostatic field part as well as the electric potential part. Now, here we are discussing about external field. So, we have applied an external field here. Okay, external field is in this direction, and what will happen inside the conductor, that is what we are interested in. Now, inside the conductor, as we said, electrons are free to move, but they are not allowed to leave the metal, right. So, if I have some conductor, I have a conductor, okay, in that conductor I have removed some electrons. That means there are some negative free electrons which can freely move, as well as there will be a positive atom left, right, positive atom which cannot move on their own, but they are still there, right. Now, what is happening when I applying external electric field? Obviously, these electrons slowly drift in the opposite direction of electric field and they reach this end. Okay, they reach this end. Okay, they reach this end. Now, what is happening here? Let us understand that. Now, this atom, positive atom, they are left alone. What they will do? They will not sit alone, they will try to move in the direction of electric field. We know that positive charges move in the direction of electric field, negative charges move in the opposite direction of electric charges. Now, electrons are free to move, they are okay, there is electric field, something is going on, some flare is going on in, so they will move towards the window and they will see what is going on outside, right. So, basically this is the window and the electrons have moved. Now, protons, they cannot move. What they will do? They will call whatever atoms are here in this side and they will call, hey, there is something going on, some procession is going on, you can go and check from the window. So, they will call the other electrons from this side. Okay. So, there are positive atoms, they will call the electrons and eventually they will transfer the positive charges on the right hand side and eventually they will become neutral. Okay. So, they do not travel on their own, but they can travel by virtue of calling the electrons from the other side, and that is what it is shown here. Here we can see that this side has become negatively charged and all the atoms on the other side they have become positively charged because they have exchanged the electrons. Okay, electrons moved in this side and the positive atoms, they call all the electrons, they become neutral in the middle and right hand side become positive, right, as if all the positive charges move to the right, that is it. But positive charges do not move, but they have removed the electrons, they have the electrons switched on. So, that is why the right hand side become positive and left hand side become negative. Now, what is happening? So, these positive and negative charges, we know that positive and negative charges create an electric field. What is the direction of electric field? Electric field is always from positive towards negative, that is the property of electric field that we have learned, that electric field will start from positive and it will move towards negative. So, this is the internal electric field, this is the internal electric field and this is the external electric field, right, E naught. E naught is the external electric field, E naught is the external electric field and this E in is internal electric field. Now, what is happening here? This internal, they will arrange such that all the internal fields, all the electron and positive atom, they will arrange themselves such that this external field inside the metal becomes 0. That means, this internal field which is opposite to that of E naught, okay, they will cancel each other and they will become 0. So, the net electric field will inside the metal becomes 0. So the electric field, even though the electric field is eventually individually not 0, but the effect, the net effect, that's what we are measuring, right. So the net effect will be still 0 inside a conductor. Remember that inside a conductor electric field is still 0. Now how can we use that? At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. This is another property. What is the meaning of that? Let us understand. So suppose we have a charged conductor. Charged conductor is this. I have already drawn one charged conductor. So I want to find the direction of electric field. So electric field on the surface of the conductor, electric field is not 0, only inside the conductor is 0. On the surface of the conductor it is perpendicular, okay, or normal. Normal is same as perpendicular. Now what is the meaning of normal? Normal refers to, if I draw a tangent at this point, this will be perpendicular to that tangent. Any point, at any point if you draw a tangent, okay, any point you draw a tangent, then it will be perpendicular. Now if it is a plane surface, for example if it is a cube, then you don't need to draw a tangent. It will automatically, if it is a charged conductor, okay, it will be automatically perpendicular to the normal to the surface. That is, any line if you draw on that point, it will be perpendicular to that line. Now the interior of a conductor can have no excess charge in the static situation. So interior of a conductor, if the situation is static, as I said, number of negative charges will be equal to number of positive charges. So net charge is 0. So net charge is 0. Net charge inside a conductor at any point of time, as long as there is no charges, extra charges flowing through them, okay, that we will discuss in current electricity chapter, in the static situation, okay, that is the meaning of static situation. So if the situation is static, that means there is no extra charges. Even if you apply external electric field, in that case also it is a static situation. Electric field is not changing, electric field is constant. That means they will balance each other, positive and negative, we have seen that. So the charge in the static situation, it cannot have any excess charge. Electrostatic potential is constant through the volume of the conductor and has the same value as inside the surface. So as I mentioned that electrostatic potential is constant, electric field is 0, potential is constant. Potential is same as on the surface. Whatever on the surface, suppose V is Vs in the surface, the same value will be inside the conductor as well. So potential is constant and electric field is 0. We have given a homework problem yesterday as related to the same concept. We will discuss that as well. Electric field on the surface of a charged conductor is given by E is equal to sigma by epsilon naught n cap. Now if you know, I already told you electric field is perpendicular, so this is the direction of n cap, right. And if you see, sigma and epsilon naught both are constant. Sigma is the surface charge density, right. Sigma is surface charge density, epsilon is the free space permittivity. So for a given charge surface, if I consider a given charge surface, suppose it is positively charged, we have removed some electrons out of the metal by some external process, okay, and I made it positively charged. So near the conductor, when the conductor, we are considering any point near the conductor, the electric field is given by sigma by epsilon naught, and since sigma is constant for this charge, we can say this electric field is basically constant. So near a conductor, very close to a conductor, the electric field remains constant. So if you go slightly far away from the conductor or come back close to the conductor, it is almost constant. You can take this as constant. Okay. Now one of the most important practice that we are using is that it is used in electrostatic shielding. We know that electric field inside a conductor is 0. So we use that property in electrostatic shielding. What is the meaning of that? Suppose I made a cage of iron, okay, solid cage of iron, okay, inside there is hollow, and if I keep some very costly equipment, Okay, suppose an MRI machine which can be inflicted by external electric field. So suppose I have a very costly machine, then if I keep it inside, then whenever how much electric storm is happening outside, how much electric interference is from outside, that will not disturb that machine and it will remain unaffected. So the thing that is inside, that will remain unharmed. Okay, that is called electrostatic shielding. So we are shielding it from any electrostatic field changes or any charge generation, that the system will remain unharmed. So there is a famous experiment by Faraday. He did he standed inside a cage, okay, iron cage, and what he did is he asked his apprentice to apply very high potential outside, and what happened is he still was standing inside. Nothing happened to him because this cage itself is preventing any charges to flow inside. So he was safe inside. It is called Faraday's cage experiment. You can Google and check. You can see in YouTube what is Faraday's cage experiment. Okay, so that is basically an application of electrostatic shielding. So any expensive equipment is stored inside a metal cover. That is the reason, because the metal cover protects it from any external electrical harm. Okay, now let us move on. You have seen this, right? You have seen this. Now tell me the answer. This is a metallic conductor and these birds are sitting on a live wire. Now why do you think these live birds don't get electrocuted? Okay, the reason behind that is nothing to do with electrostatic shielding or anything. It is just a extra question that I wanted to discuss, that these birds have very high resistivity, and when they are sitting on a single line, everything is at same potential. Okay, when they are at same potential, electric charges cannot flow. Electric charges cannot flow means they are safe. Now this is the very basic explanation. There is a complicated explanation on that that we are not going to discuss in this video, but if we try to do the same thing by holding our hand, then we will not survive, because our body is a good conductor and electricity will flow through our body and we will die. Okay, so don't try it on your own. It is a life threatening process, so don't try to do it. Okay, now let us discuss the homework problem that we have given in our yesterday's video. A conducting sphere of radius r is given a charge q, the electric potential and electric field at the center of the sphere. So I was just discussing that there is a sphere, we have given some charges. Charges will always stay on the surface of the conductor. Okay, and on the surface of the conductor, electric potential is given by, what is electric potential? Potential is given by 1 by 4 pi epsilon naught, okay, q by r, right? It is constant. It does not matter if it is on the surface, the same value will be on the center. Any point in the inside, electric potential will be this value, and electric field inside the conductor is 0. Now you have to check the order of the question. What is mentioned? Electric potential first and then electric field. Okay, so electric potential is q by 4 pi epsilon naught r and electric field is 0. So correct option is option D. You have to be careful. Okay, if electric field was first and electric potential was next, then the correct answer would have been A. So don't get confused. You have to read the question before answering. You have to be sure. Okay, first part is potential. Potential is not 0. Potential is q by 4 pi epsilon naught r and electric field is 0. So electric field is 0. I have mentioned whoever answered this question correctly, I have mentioned that in my during when I was taking the comments, I have mentioned marked. Okay, if it is correct, I have given a thumbs up as well. Now what is the second question? Work done carrying an electron from point A to point B in an electric field is 3.2 times 10 to the power of minus 18 joule. The potential difference VB minus VA. Now this question, the options given was incorrect and none of you have tried to answer it. I have not seen any correct answer till I am here recording this lecture. No one has answered this correctly and no one even tried to mark the inaccuracy in the question. So what is the question? Question is the work done is given. Okay, work done is given 3.2 times 10 to the power of minus 18 joules. Okay, and they have asked you to find the potential difference. Now we know that work done is basically difference in energy, right? Potential energy, that is delta U. So delta U is 3.2 times 10 to the power of minus 18 joules, right? This is the potential energy. Now what we are trying to find? We are trying to find the potential difference. Potential difference delta V, they have written delta V, V minus VA, that is same as delta V. Potential difference is nothing but the potential difference is given by, we know that, potential energy divided by the charge, right? So what is the charge? Charge is an electron, right? So potential energy is given as 3.2 times 10 to the power of minus 18 divided by charge of an electron, that is 1.6 times 10 to the power of minus 19, right? Now that will be cancelled, it will be 2 times 10 minus 18 divided by minus 19, so it will go up and it will become 10 to the power 1, so it will be 20 volts. Okay, 20 volts. So none of the options are correct. Okay, 20 volts is the answer. So if the same question comes in the same format, then obviously it is a bonus question, but this question will not come in like that. Those who are forming the question, if they give this question, this type of question, they will give you the correct options. Okay, now let's move on. Let us talk about dielectrics. What is a dielectric? Dielectric basically a fancy name for non-conductors or insulators. Okay, simple. Dielectrics is nothing new. We already learned about non-conductors, insulators, right? So this is a fancy name for them. So dielectrics are non-conducting substances. As I mentioned, this is insulators. In contrast to conductors, they have no or negligible number of charge carriers, that is free electrons. They don't have any free electrons. Okay, almost zero or very negligible, right? What else? Now if you subject to this inside a electric field inside a conductor is become 0, because we know that electric field E0 plus E inside equals to 0, right? So basically magnitude wise E0, magnitude wise we can write that magnitude of inside is equals to magnitude of outside, right? Sign is opposite but magnitude is same. Now what will happen if we subject dielectric in case of external electric field? In case of dielectric, see, the internal, there will be an internal electric field, they will distribute the charges, but since they are not conductors, they will not be fully able to repel the external effect, and they will only be able to repel it by small amount, and the total electric field inside the dielectric will not be 0. So basically in case of dielectric, E in magnitude wise not equals to, in fact we can write this as E inside is less than that of external electric field. So it will not be able to cancel that. So E out will still dominate by some margin, okay, based on the property of dielectric, how good it is a dielectric. So they will not be able to cancel the internal electric field, and they will have some amount of residual external electric field inside them. Okay, so they will allow the electric field to pass through them, but not entirely. Suppose I apply 2 Newton per coulomb electric field, then maybe it will reduce 0.5 of that, and 1.5 will still pass through that. Okay. Now it turns out that external field induces a dipole moment by stretching or reordering. We will discuss that in a while. Okay, reorienting the molecules of the dielectric. The collective effect of all the molecules of dipole moment is net charges on the surface of the dielectric, which produce a field that opposes the external field. So it will also oppose, this internal field will also oppose the external field, but it will not be sufficient to cancel the effect of the electric field, right? The opposite field is so induced that it does not exactly cancel the external field, it only reduces it. So very important, it cannot cancel the external electric field, it only reduces it. The extent of the effect of the it depends on the nature of the dielectric. Now, how good is the dielectric? If it is a very good dielectric, it will reduce it. Now, dielectric is something what we are wanting, right? So, good dielectric will reduce it by small amount. Bad dielectric, that is which is very close to conductor, it will reduce it by a high amount. Okay. Now, let us talk about dielectric constant. Okay, dielectric constant is also known as relative permittivity. Very important, it is also called relative permittivity. You may heard the term. Okay, dielectric constant is generally represented by a capital symbol K and also sometimes epsilon r. Epsilon r, that is relative permittivity, and dielectric constant K, they are same thing. Okay, they are same thing. Now, dielectric constant or relative permittivity is permittivity of the medium divided by permittivity of the free space. So, permittivity of the medium means how much electric field it can allow through it. Okay, how much electric field it should allow through it, that is the measurement of the dielectric of the permittivity of the medium. So, how much it is permitting, okay, and how much is the permittivity of free space. Free space, we know that free space dielectric constant, we already know the value, etc. So, if you put that value, whatever the ratio is, that ratio is called a permittivity of or dielectric constant of that medium. Now, this is very important concept. We are going to use this value from now on very extensively. Let us look into a numerical problem, not numerical, just basic conceptual problem. Two charged spheres separated by a distance d exert a force F on each other. Okay, if they are immersed in a liquid of dielectric constant K, then what is the force if all other conditions remain same? So, what is the question? We have two charges, say Q1, say Q2, and in the air they are initially separated by a distance d and the force between them is F. So, F is the force between the two charges when they are separated in air. Now, I took the entire thing and I immersed them into a dielectric constant. Suppose water. Suppose water is a dielectric medium. I took this thing and I immersed it in the water. So, the distance remains same d, charges remain same Q1, Q2. Okay. Now, what will be the force? What will be the new force? That is the question. Now, to answer that question, you have to go back to Coulomb's law and understand this. In Coulomb's law, we know that force is given by 1 by 4 pi. If you write down the Coulomb's constant explicitly, Q1, Q2 by d square, right? That is when they are kept in air. Now, when you are immersing it into a liquid or dielectric medium of constant K, now what is changing? Which of the following quantity is changing? Q1, Q2 are not changing, D is not changing, only thing that is changing is this epsilon naught. This was for free space. Now, is it in free space anymore? This is no longer in a free space, right? So, what is happening here is, in that case, suppose the force is F dash, we can write this as 4 pi epsilon Q1 Q2 by d square. Now, what is epsilon? Epsilon is the dielectric permittivity of that medium. Permittivity of that medium. Now, we know that permittivity, dielectric constant is permittivity of the medium divided by permittivity of free space. So, what is epsilon? From there we can write epsilon is basically K times epsilon naught. So, you have to put that value here, 1 by 4 pi K times epsilon naught Q1 Q2 by d square. So, it will be 1 by K times F. So, if you take the K out, it will be same as F. So, it will be F by K. Okay. So, the dielectric constant, the new force will be F by K. So, what is the correct answer? Correct answer is option D. Be careful if this kind of question is asked. It is very simple question. Maybe you will feel what is the answer. So, if you know that whenever it is immersed in a dielectric medium, the force reduces by divided by dielectric constant. Now, let us move on. Let us look into one more problem. dielectric constant of a metal is, there are few options: 0, infinite, constant, unpredictable. Okay, let us look into the another definition of dielectric constant. So, dielectric constant is basically given by E applied divided by, or this is too long, let me write in short, E applied electric field, we call it naught, right, and what is the E naught minus E in. Okay, how much it is reduced, what is the net value inside, right. Now tell me the answer. What is the value of E naught minus E in for a conductor? For a conductor it is 0, right. So, E naught was applied, right, E naught was applied and it was reduced to 0. So, E naught by 0. So, basically this becomes infinite. Okay. So, the dielectric constant for a metal is infinite. Okay. You remember this value, remember this answer. Okay. This is a very common MCQ for your board, and maybe they will ask you in your KCT, your KCT paper is easy. Okay. Now, dielectrics are classified into two part, one is polar, another one is non-polar. Okay. So, polar and non-polar are the two categories of dielectrics. Now, let us look into the non-polar first. In a non-polar molecule, the centers of positive and negative charges coincide. I will explain that in a while. The molecules then has no permanent or intrinsic dipole moment. Examples of non-polar molecules are oxygen, hydrogen molecules, which because of their symmetry have no dipole moment. So, let us understand that we have, suppose, an atom, hydrogen atom. We are considering atom now. Okay, same logic can be applied for molecules as well. Hydrogen atom, one proton inside and one electron is orbiting around it. Okay. Now, what is the center of the positive charge? Center of the positive charge is the center of the atom. Now, in this case, what is the center of electron or negative charge? Center of electron, you will say the center of the negative charge is here. Are they coinciding? No, obviously not. They have a distance. So, they are actually like a dipole. But is it the fixed position of the electron? Obviously not. We know that electrons do orbit around the nucleus in a very high speed. Okay, and we cannot exactly locate the electron. We can only find its probability, and that probability lies equally in the entire orbit, right. So, electron can be here, 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 electron can be at any place. Now, what is the average position of the electron then? To find the average, we have to find all these lines, draw all the lines, and then I have to find the cross section of this line. So, cross section, again if you see, it is crossing at the center of the atom. So, the electrons, because it is rotating, not because it is at the orbit, because it is rotating very fast around the orbit, okay, the average location of the electron will be at the center of the atom. So, this is called the symmetry. Because of the symmetry, the orbit is circular in nature. So, because of that, we will get a symmetrical structure. Now, same thing will happen if you are considering a molecule. Okay. So, molecule, suppose there is a molecule in hydrogen molecule, there are two atoms. Okay. So, this center has at the center of this hydrogen atom, this has a center at this point. So, what is the average distance? Average distance will be here. So, at this point, both positive and negative will coincide. So, the center of positive and negative will coincide, and we will draw this as, we generally draw that part like this. Okay. The diagram for non-polar molecule is this. So, they are centers of positive and negative, they coincide with each other. Now, if there is no separation between positive and negative, then what is the dipole moment? Dipole moment, we know that dipole moment is P times charge, any one of the charges divided by the distance. Now, the distance between them is 0. So, their centers coincide. So, distance 0 means dipole moment is 0. So, they have no dipole moment. This is called intrinsic dipole moment, that is whatever they have by default, whatever they have from the beginning. So, that is called the dipole moment. So, dipole moment is 0 for a non-polar molecule. Okay. Now, let us look into the polar molecules. Polar molecules is the one which center of positive and negative charges are separated even when there is no external field. Such molecules have a permanent dipole moment, and ionic molecules such as HCl or a molecule of water are examples of polar molecules. So, I have already explained why HCl is a polar molecule. So, HCl, okay, they share 2 electrons, okay. 1 electron is given by hydrogen, 1 electron is given by chlorine. Now, what is happening, because of higher electron affinity, this electron pair says I will not stay in the middle, I will go towards chlorine, okay. So, chlorine becomes delta minus, okay, negatively charged, and hydrogen become positively charged, right. Now, they are not at the same position, they are separated by a distance. So, their dipole moment is not 0. So, they have a dipole moment, okay. P equals to delta plus or delta minus, whatever you take, but just the value of delta, we are not interested in the magnitude, times the distance, whatever the distance, 2a, right. This is the dipole moment, permanent dipole moment of any polar molecules. Similarly, it is applicable for oxygen also, okay. I hope that that is explained in your chemistry class. How oxygen is a polar solute. Now, in case of physics, the dipole moment is from negative to positive. In your chemistry class, maybe they have said this is from positive to negative, they take the opposite direction, okay. So, they use negative dipole moment, whatever we are talking about, okay. But they have a permanent dipole moment. So, their centers of positive and negative does not coincide, and they are represented like positive and negative. They are represented like that. So, if I draw this, that means it is a polar molecule. If I draw that one, whatever I have drawn in previous class, previous part, this one is for non-polar, this is for non-polar, and this one is for polar, okay, clear. Now, what will happen if I subject this non-polar and this polar material in external electric field? When the electric field is 0, obviously their centers are coinciding, that means there is no net dipole moment. In case of non-polar molecules, even though the net electric field is 0, they have a molecular level, at molecular level they have a dipole moment, but they are oriented such that they are cancelling each other, right. This negative is close to this positive is close to another negative positive, so that net dipole moment was 0, net electric field was 0, okay. So, the net electric field was 0, but when we applied an external electric field, when we apply an electric field, what happened to metals? Remember, same thing happened for our non-polar molecules. The negative charges orient themselves, so direction of electric field is in this direction, okay. Electric field is applied in this direction. So, negative charges will slowly move in the opposite to the electric field, and positive charges slowly move in the direction of electric field, okay. So, your left hand side will become negative and right hand side will become positive, same as what happened in case of metals. Now, in case of polar molecules, based on the strength of the electric field, if the electric field is not very strong, some of the charges will orient, okay. So, you see the negative charges is still on the left and positive charges still on the right, okay. Some of the molecules will orient themselves according to the applied electric field, okay. Whether a polar or non-polar, a dielectric develops a net dipole moment in the presence of an external field. The dipole moment per unit volume is called polarization and is denoted by capital P. For linear isotropic dielectric, polarization P is given by epsilon naught chi e, okay. E vector, vector E, that is electric field. Now here chi E is a constant, okay, remember this spelling, it is chi, okay, okay, it is like x, okay, and this is chi. It is not exactly a x, it is a one arm of the x is little curved, okay, and some people draw it like this also, that is also fine, okay, and this is called chi. So symbol chi, okay, Greek letter. It is a constant characteristic of the dielectric and is known as the electric susceptibility of the dielectric medium. This is the electric susceptibility. Now if you are using this formula, this chi E is unitless quantity. Now if you are using a different formula where you are using P is equals to only chi E vector, okay, one new problem came on this formula in our previous year question paper, okay. If you have seen my solution of previous year question paper, you will know, okay. By here polarization is polarization per unit volume, okay, P is polarization per unit volume and E is electric field, then you can calculate chi E like this, okay, remember this formula. Now the polarized electric dielectric is equivalent to two charged surfaces with induced surface charge densities, say sigma p and minus sigma p. The field produced by this surface charges opposes the external electric field. The total field, everything we are already discussed, everything. Only thing is we can consider, suppose this is a dielectric medium, it is polarized or non-polar, polar or non-polar does not matter. When you apply an external electric field, what happens is that they organize themselves like this, I already mentioned that, and you can consider they are basically two charged surfaces. What are those two charged surfaces? One charged surface is negatively charged surface with surface charge density minus sigma p, and this is a positive charge surface. In between there is nothing, in between there is neutral part, so there is nothing in between, and this you can consider positively charged plate with sigma p dielectric surface charge density, okay. Now the total field in the dielectric is thereby reduced from case where no dielectric is present. Obviously if there is no dielectric and when you insert a dielectric, the electric field inside a conductor, suppose there is a conductor, between the conductor you place the dielectric, it will reduce. We should note that the surface charge densities plus minus sigma p arises from the bound charges. What is the meaning of bound charges? Okay, bound charges means which are not free. These charges is not you cannot take these charges and take it outside, you cannot take them with you. If you want to take a negative charge, you have to take the positive charge as well. So they are not bound charge, they are not free charges, they are actually bound charges. Bound means they are not free, they are inside the dielectric, okay. Now time for today's homework problem. So this is the homework problem number 1. Pause the video if you want, read the question, try to solve it, okay. I will be this is fine. The potential energy of the system, they have asked you to find the potential energy of a system. You need to look for the answer, try to solve the answer. Even if your answer does not match with the given options, given A, B, C, D options, you can mention whatever the answer that you have found, okay. Pause the video, read the question, try to answer that. Next question, this is very simple question. Again pause the video, read the question and try to answer this question. We are going to discuss these two solutions in our Monday's video. In Monday we are going to discuss about capacitance, very important. So don't miss that lecture where we are going to discuss capacitance, and this all concepts that we have learned from dielectric chapter will be applied there. Also again I am repeating that if you have not yet subscribed to our playlist, you can go and click on the playlist and you can click on the bell icon. Whenever we are adding any video, you will get a notification. Also you should join our WhatsApp channel, the link is given in the description. Tomorrow, very important, tomorrow is your first KPL test series, KSET Premier League, that we are starting on every Sunday 10 a.m. we will be giving you one question paper of physics, 30 question each. You have to answer all the 30 questions and see if you are correct or wrong. In the evening I will be uploading a video. Okay, you can check the entire series how I am solving all those 30 questions, or you can check whatever questions that you have doubt. If you have answered the question maybe correctly, but you are not sure how this question is correct. And one more thing I request you, do not cheat. This is for your own benefit. So do not cheat till you have the time, till 6 p.m. you try to solve it on your own. Once the time is passed, once my video is uploaded, then you can check the answers. Okay, so do not cheat. This is for your own benefit. We are not going to sit there and ask you, okay, you are cheating. So this is up to you. You are adult enough, you can do it. I have confidence in you. So all the best for tomorrow's exam. And if you have not yet subscribed to our YouTube channel, don't forget to subscribe to our YouTube channel. I thank you for watching this video. We'll be back with a video tomorrow. Thank you.